All right, guys, today we are going to graph the tangent function. All right, we're going to graph the tangent function. Now, tangent is a little bit more interesting than the sines and cosines. One thing that makes tangent more interesting is the fact that the domain is not all real numbers. Okay, since the domain's not all real numbers, we're going to have some interruptions or some breaks in our function, which is kind of interesting. It makes it fun. But we're still going to start it the same way. So think back to yesterday. When we graphed tangent yesterday, not tangent, sine and cosine yesterday, we started by plugging in 4 specific values or 5 specific values, and then we went into the opposites. Does anybody remember what numbers we plugged in yesterday to start our graph? Pi over 2. What else? Pi. What kind of angles did we use? We plugged in the quadrantals. So we're going to do the same thing today for our tangent graph. So I have my x and y axes to start. Okay. I'm going to put a couple tick marks on here. So whenever I do 4 tick marks, I go out, I do that one first. I put one in the middle and then one in the middle of each of them. So I know that they're about equally spaced apart. Got one here, middle, and midpoint of each of those. Got that right there. Now, I could put maybe 1, 2 on the y-axis. All right, so I have my 2 axes, y or f of x, whatever you want to call it, and my theta axis. Some books use x instead of theta. Really doesn't matter. We can label our axes exactly like we did yesterday, so if you want to fill those in, you can do that. Now, same reason as yesterday. The reason we pick these angles is because more or less this is where all the cool stuff happens. But with tangent, we might want to check in between them, and there's a quick way to do that, so we will talk about that in a little bit. Normally when we draw the graph of tangent, just like yesterday as well, we usually just draw 1 complete cycle or sometimes 2 complete cycles. And I usually start at 0 and go towards 2 pi. But for practice right now, I want you guys to see the negative side of the theta axis as well. So we're going to kind of do a little bit of extra graphing. Okay. Tangent in your head, or maybe you have the values already memorized. Tangent is sine over cosine. So when you're figuring out tangent values, yes, you could think of it as sine over cosine, or maybe some of you have already kind of memorized the tangent values going around the unit circle. Either way, we're good to go. So if I take this tangent of 0, what do I get? Tangent of 0. You get 0. All right. Tangent of pi over 2. You're right, it's undefined. How do you indicate a function is undefined on its graph? How do you show that? Sometimes there's an open circle, but the open circle is what we call a removable discontinuity. We use those when you can cancel the problem from the top and bottom. In this case, I can't cancel something from the numerator and denominator to remove the discontinuity. Removable discontinuities are holes. If I can't remove it, think of the graph of 1 over x from last year. X is not allowed to equal 0, right? What does the graph have at 0? 1 over x.
It's a line, man. You can't go there.
That line, you can't go there. It has a special name. What's that line called? It's a vertical something.
Asymptote.
Wow, look how smart that epiphany was. A vertical asymptote. So what we're going to do is we're going to fill in a little vertical asymptote right over here at pi over 2. That's undefined. Can't go there. We block it off. It's like caution tape. Okay? Next, what is the value of tangent at pi? It's also 0. What's the value of tangent at 3 pi over 2? It's asymptote. It's undefined. So we put an asymptote there. Tangent of 2 pi? 0. Do you see a pattern? Okay, so you should be able to fill in some more markings on this graph. So we have a few more zeros, x-intercepts, and we have a few more asymptotes. Now, obviously, these go on forever, ever, and ever, right? Now, I need to draw my graph in, but I don't really have enough information right now. Last year, you guys graphed rational functions, and you probably used the fact that the exponents were even or odd to decide if your graph would bounce off of the x-axis or cut through it. But here we don't really have polynomials, so we don't really use that same strategy. The space between 0 and pi over 2, that's really representative of quadrant 1. What kind of output does tangent have? What kind of ratio will tangent have in quadrant 1 between 0 and 2 pi? What kind of answers will you get in that quadrant? Positive answers. All right, so that means my graph is going to go in that quadrant, and asymptotes, well, those are there for us to approach. So you'll get closer and closer and closer to that asymptote from left to right. Now, quadrant 2 is between pi over 2 and pi. Now, you could think of this a couple ways. For starters, the answers for tangent in quadrant 2 are actually the opposite of the answers in quadrant 1. They're also what kind of numbers, basically? Negative numbers. So what we could do between pi over 2 and pi is we can draw that same kind of shape right over here. It's negative in this quadrant. In quadrant 3, the tangent values are the same as the tangent values in quadrant 1. So I'll actually have the exact same picture repeating itself. Then in quadrant 4, between 3 pi over 2 and 2 pi, it's the same as quadrant 2. Now, tangent. Is that symmetrical? Was that an even function? Should I have the same picture on the other side, reflected over the y-axis? Or was it an odd function, where if you rotate it about the origin, then you get the same picture? It was odd, from the even-odd properties. This is between negative pi over 2 and 0. That's basically quadrant 4, so it should match that. Over here, it's more or less quadrant 3. Then, before that, if we go backwards, it's going to land in quadrant 2. And this is quadrant 1 again. Now, this is a whole lot of tangent. When we graphed sine and cosine yesterday between negative 2 pi and 2 pi, we had 2 complete cycles. How many complete cycles do I have now?
3.
Count again. All right, not 3. Not 5. Not 2. How many?
4.
Yes, there's 4. If we start here, this, the asymptote, and then this guy, that is 1 cycle. Do you see another one right here? Do you see another one right there? And another one in here? Question?
I broke my pencil. Can I sharpen it?
Here you go. Some extra pencils. All right, so those are 4 complete cycles. That being said, all right, this being said, what is the length of 1 period for the tangent function?
1 pi.
Just pi, okay? So sine and cosine, their period was how long?
2 pi.
Good, but the period for tangent is just pi. So the formula for the period, what do you think that's going to be? Pi over b, exactly. So that's going to be the formula we use when our b value is something different. Okay, now there's a couple other things that we can talk about. If we look at this with tangent, we go from a 0 to an asymptote to a 0 within 1 period, right?
Yeah.
So do I need to find a quarter of this period? No, I need to find what fraction of the period to get my tick marks? I have to find half of the period. So we're going to find h for this one, which is half of the period. So you just multiply it by a half this time. Now, could you go about doing this the exact same way as sine and cosine and do 2 pi over b, break it into quarters, and just graph 2 cycles? Yes. The problem with that is later on, there are questions about the periodic behavior of tangent. And if you think that a period of tangent is 2 pi, you're going to get the wrong answer. But can you get the right graph by mimicking what you did for sine and cosine? Yes. But you'll mess up other questions, all right, about the behavior of the graph and the periodic and the cycles, all that, you'll get those wrong, okay? So just keep that in mind, that you could still find a period using 2 pi over b, even though it's not truly a period, and you could still get all the tick marks or spaces by doing a quarter of that period. And I might not know you're doing it incorrectly, but when I ask you a question about the period, or if I ask you a question about how far apart things are, you're going to get things wrong. So just be careful on how you want to handle that, okay? Now, one thing I did to remember this when I was a junior in high school doing graphs of trig was I used to remember the word tan I associate with summertime, right? Because you're tan in the summer. And you have to check your pH level of your pool. Make sure you could go swimming. So the pH is the period and the half period. I'm a weirdo. You guys already know that. All right? So there's that option. And I would also remember, this one's even worse than that, if you thought that was bad. In the summer, it's bathing suit season. You don't want 2 pies. You only eat 1 pie because that's just too much pie for summertime, okay? So 1 pie in the summer. Really, maybe no pie, but if you need a way to remember. Okay, now, one other thing I want to address is the fact that there are more points, and I'm kind of not graphing everything right now, but what's exactly between 0 and pi over 2? That blue tick mark right there. What is that angle? Pi over 4. Pi over 4 is a goodie for tangent because it's easy to do. What's the tangent of pi over 4?
1.
So this right here should be pi over 4 comma 1 if you think about it. This guy over here, between pi over 2 and pi, what angle is that? 3 pi over 4. So this dot is at 3 pi over 4 comma what? -1, exactly. Over here is what angle between pi and 3 pi over 2, the midpoint? 5 pi over 4. And what's the tangent of 5 pi over 4? 1. So it's up there again. And between 3 pi over 2 and 2 pi is 7 pi over 4, which gives us the output of -1. Okay? Now, the only time that really becomes significant is if we were to do a vertical stretch or compression, all right? Because normally you wouldn't see like an amplitude change. Do you see there's no amplitude in a tangent graph? So if you wanted to show a stretch or compression, I would use those blue points to show that happening, okay? Are you picking up what I'm putting down?
Yeah.
Maybe a little? All right, so we're going to do an example right now of graphing tangent. All right, I'm going to write it on the board. I'm going to pause recording, and then we're going to check answers, okay? So let's make one up. Let's do example, because this is example 1 today. And we'll do f of x equals, we can make it up together. Let's pick out some favorite numbers.
2.
So do you want it to flip over the x-axis?
No.
No, not ready for that? All right, but we'll put a 2 out front. We'll stretch it. 2. It's going to be tangent. All right. Now we're also going to, let's do a horizontal stretch or compression. So do you want to be stretching it horizontally or compressing it horizontally?
Stretch.
You want to stretch it? So if we stretch it, let's say we stretch it by factor of 3, what number goes in there?
1/3.
1/3, good. All right. Now let's shift it. Do you want to shift it to the left or shift it to the right?
Right.
Right's always easier, so we put minus. How far? Let's pick different numbers. We used 1, 2, and 3 so far, so. 4. 4 whole units? How about pi over 4? Otherwise, you're going to have to use pi plus 4, you know what I mean? Or 0 plus 4, pi over 2 plus 4, things like that. That's kind of weird. You want it in increments of pi. And let's move it. You want to go up or down? How far?
2.
Well, we already used 2.
5.
Beautiful. Amazing. All right, so I'm going to pause the recording, and we're going to try it, and then we'll check in with each other and see if we got the right answer. So if you're watching, you can pause. All right, so this is the graph I got for my tangent function. And I had that my graph shifted to the right pi over 4, which is why I got that as my starting point. So everyone agree with that? Okay. Next, I know my graph shifted up 5 units. That's why I have this dotted axis, midline sinusoidal axis at 5. Are we okay with that? Okay. So that's where I started. From there, I also looked at the 2 out in front. That's my amplitude. And while it doesn't really seem to do too much in a tangent graph because of its shape and behavior, it does affect it. It is a vertical stretch. So normally at these blue marks right over here, which we talked about on the parent function, my tangent graph would go up 1 unit or down 1 unit, up 1 unit or down 1 unit. But because of the stretch of 2, I just wrote on my y-axis that I'm going to go up to 7 and down to 3. All right? So that's just how I showed my vertical stretch. I didn't even label those tick marks in between. I just wanted to sort of indicate that I know it stretched by a factor of 2 in the vertical direction. Got me?
Yeah.
That's why I drew those there. All right, next. The other thing I have to consider is my b value. And the b value is 1/3. 1/3 will give us a horizontal stretch by factor of 3. When I divide by 1/3, I'm actually multiplying by 3, and that's how I got that the period was equal to 3 pi. From there, we found a half period, which is 3 pi over 2, and then I made it 6 pi over 4, so I'd have a common denominator. I added 6 pi over 4, and really I could stop at 13 pi over 4 and draw 1 complete cycle of tangent, but I opted to draw 2 cycles, so I went all the way until 25 pi over 4. So adding 6, 1 plus 6 is 7, another 6, 13, another 6, 19, another 6, 25. So I know I did it right. Another reason why I don't reduce. I like to just see my fraction so I could see if I'm adding by the same amount each time. Question?
Yeah. How do you know, like, that 7 pi over 4 is going to be your asymptote?
Okay, so really what I'm doing is I'm taking the graph we see over here. So I took this whole entire graph and I stretched it out like an accordion. So I stretched it by a factor of 3 and I moved it to the right. So my normal amount, my normal period was pi. And since I used that pi in my equation, pi over b, and it gave me 3 pi, and then I cut it in half for the 6 pi over 4, I know every time I jump, I'm going to land at that same pattern of values. I'm going to land from a 0 to an asymptote, to a 0, to an asymptote, to a 0. It just works like that every single time. It takes the parent function and manipulates it, okay? Oops, sorry, I didn't mean to go there. Now, you know how we had the omamos and the mom-moms?
Yeah.
Well, we could also kind of look at our own little patterns for this guy over here. If you wanted, it's no omamo and it's no mom-mom, but we go from a 0 to an asymptote, to a 0, to an asymptote, to a 0. So instead of using the O's, because that would be O's and A's, and how do you even pronounce that? I use ZA, so I have zazaz for tangent. 0 asymptote, 0 asymptote, 0. And that's really 2 complete cycles. Zazaz. So tangent has zazaz. Okay? I drew in my branches because it was positive, so I went up first, then down, below the sinusoidal axis, above it, and then below it. Now, what else do you think we're going to have to find for these graphs? Yep. So let's start with the domain and range of the parent function. So we're going to go back for a second to the parent function right over here. The domain is interesting because I can't equal all real numbers. It's a little bit more work now. So my domain started off as all real numbers, but then what happened? We lose some, right? So all real numbers such that theta cannot equal. Now, it doesn't matter which asymptote you pick. I tend to pick my first positive asymptote or non-negative asymptote. So where is my first non-negative asymptote? Pi over 2. So theta cannot equal pi over 2 plus, now how far apart are my asymptotes? They're pi. So that's why it's plus pi n, where n is an. So n exists in the set of integers. There's my domain. Makes sense for the domain we found the other day. But now you have a picture for it instead of just trying to figure it out from the unit circle. Now we have a visual representation of it, which makes it a little bit easier. All right, now the range, we also kind of figured out range conceptually the other day. What's the range? Looking at this picture. All real numbers. So you could use that R, or we can use interval notation, negative infinity to infinity. So if I go over to this example, and I try to figure out my domain and range, it's going to be a little bit different. The same concept is there. Domain. The domain is all real numbers, such that theta cannot equal who?
6 pi over. Wait, 7 pi over 4.
7 pi over 4, good. Because that's my first asymptote. 7 pi over 4 plus, how far apart were they? No, I heard someone say it. 6 pi over 4 or 3 pi over 2. Either way. A half period? Is that where the next asymptote is? No. How far is the next asymptote?
3 pi.
Boom, it's over there. Not at the next marking, right? So how far apart is 7 pi over 4 and 19 pi over 4?
3 pi.
Which is 12 pi over 4. That's another reason why I don't reduce my fractions, because sometimes they reduce all sporadically, and then you want to find out how far apart they are, and you have to do more work. If you leave them with the common denominator, it's quicker to find out how far apart they are, okay? So from 7 to 19 is 12 pi over 4, which is 3 pi, or basically the entire period. So it's 7 pi over 4 plus 3 pi. What goes next to 3 pi? N, comma, nes. N exists in the set of integers. Boom, there's your domain. Last, the range.
All real numbers.
Just going to squeeze it over here. I don't have room for interval notation. That's all we get. Easy? Not easy, but too challenging? Not too challenging yet. All right, so what we have now is 3 trig functions. Sine, cosine, and tangent. Can you memorize them? Sure. Ms. Bennett said when she was in college that most people just memorized the graphs because no one took the time to teach them how to graph them. And it's a huge, huge struggle. You guys, however, will be able to figure them out on your own. But I want you to take a second and we're going to try to graph someone new right now. Who do you think we're going to graph? We already did sine, cosine, and tangent. Yeah, we're going to graph cosecant. So I want you, using your brains, to see if you could put together the graph for cosecant. You're going to set it up from negative 2 pi to 2 pi with the quadrantals. And if you can do cosecant, you get a brain eraser. So, on your mark, get set, go. Pausing the video. All right, so this is the skeleton for my graph of cosecant. I know it comes from sine. It's the reciprocal of all the sine values. So just quickly, everywhere that you have a 0, your cosecant graph will have a what? A vertical asymptote. So everywhere I had an asymptote, everywhere I had a 0, I'm drawing in a vertical asymptote. From there, all of my extremely big values, my maximums, will become more or less minimums, okay? So all of my maximums basically will become minimums. This was the highest point. If this was 1/2 between 0 and pi over 2, there was a 1/2. Now it would be a 2. Do you know what I mean?
Yeah.
So it goes up like this and approaches the asymptotes. This guy, 1 over 1 or negative 1 over 1, it's still negative 1. Same idea, right over there. And lastly, we have this guy right over here. So it's all about the reciprocals, and we would do domain and range the same way. So for homework, I want you to write the domain and range for this function, and I want you to graph the following function. Are you ready? Domain and range for the parent, and your homework is y equals, let's do some fun numbers, negative 1/2. Cosecant. Now let's be a little bit more creative. Let's do 2/3 theta minus 5 pi over 6. Now pay attention to the fact that I don't have an extra set of parentheses there. So you have to do a little factoring. Plus, let's do 1. So you're going to graph that and do its domain and range, and someone's picture is going on the board. Bye.